computer. We'll share the screen. And okay, looks like I have somebody new on the group. Mr. Gray?
Yes, good morning.
Good morning. Welcome to the group.
Thank you.
Unfortunately, you're coming in the middle of, this is lecture 11. So you've missed the first 10.
Okay.
And there's a lot of material that's been covered. We started with experimental thermodynamics and moved on to statistical mechanics, and then we've moved on to information theory, which we've done quite a bit on Shannon's stuff, including coding theory, channel theory, and today we're going to repeat at least the material that we did last time on Huffman codes, a way to shorten codes, and then move on to error correcting codes. So if you get lost, please ask questions as we go along, because there's a lot of material that we've covered before. So please ask questions all the time, interrupt constantly. That's the idea, okay?
Okay. I'm interested in whatever you have to offer.
Okay, and I would ask you, like everybody else has, to please mute your Zoom. Okay, can everybody see my notes here? Switch to keyboards.
Notes are on.
Okay, good. There. All right, finally I have my mouse, and we've gone through the, for some reason it's doubling everything. I don't know why that is. Okay. So I will not use the mouse, I will use the arrows. Okay. So we're on to chapter 11. We're going to review the material we did last time on Huffman codes, which I thought I did a very poor job of explaining. So I've tried to go through the material we did last time and then increase some explanations about how it actually works, because I thought I did a terrible job last time. For which
Someone else's audio. I can't hear Bob.
Oh, can everybody hear me? Oh,
You just came back.
I can.
Yeah, it says my internet connection is unstable. So I apologize. All right, so we've been talking about the general channel description. You start with a collection of messages, which we've generally focused on an alphabet, but we've also talked about working with sets of words, because the English language is, for characters, is very context dependent, and also has a very different probability distribution for different words. So by making a Markov channel, Markov model, what was it? There's actually a name which I'm forgetting, but we went through how you can build a mathematical model of the next character come out, or the next word, and that's a Markov process, and we can use the probabilities that we know from the English language and get much better description of what's more likely to happen. And those kinds of structures are what are used in spell correctors. So we looked at Shannon's first fundamental theorem, second fundamental theorem about communication channel throughput. We talked a little bit about noise error, and coding theory, which is what we're focusing on now, includes both compression codes, which a Huffman code is a compression code, and error correcting codes, which we're going to come to today, Hamming codes. And we will use this to show that you can compress errors, compress data, and then somebody is using their mute. Would you please mute it?
We know that among the choices.
Okay. This is still on.
Yeah.
Still on here. Turn it off.
Wait,
I don't know who's doing it, but please. Great. Thank you. No, you're still doing it. Please mute.
It says iPad, maybe an iPad.
Yeah. All right. They finally muted. Okay. We might discuss a little bit about cryptography later, but the whole process is different. The meaning here is to make sure that messages are unreadable except to intended recipients. So but many of the techniques are common. All right. The original design of codes was actually to make messages hard to discover, and therefore cryptography. However, in the 19th century, we developed the electrical telegraph, first the optical telegraph, and which we talked about last time. And they were ways to, we talked about the Morse code, and the Morse code was dots and dashes and a pause. And we discovered that because, for example, a dot and a dot, dot, dot all had the same prefix, you couldn't decode which one of them it was, which is why the space or asterisk here is a symbol that separates each character. Okay. So again, there's a few examples. A goes dot dash. E, which is the shortest one, goes dot. S is dot, 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 etc. So SOS goes to dot, 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 space, dash, 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 space, dot, dot, dot. And because of the space, you can decode every sequence when you receive the special space. Okay, so Morse's system was intended for human beings because there were humans that were working on it was your fingers and wrist, on your hand in typing these symbols, and they were limited to the amount of work you could do in your fingers, and that limited everything. So that was the reason that he designed the code to follow the use of the characters in terms of their probability of occurrence in the English language. And another influential code was the ASCII, developed in the 1960s. And this used two symbols, a 0 and a 1, often called a bit. And all codes had a fixed number of 7 symbols. So there could be 128 possibilities, but 0, 0, all zeros, and all ones were not used, and therefore only 126 codes were allowed. This was greater than the number of symbols Morse code could do. Okay, so here's typical ASCII codes, and if we have 2 alphabets for coding A and B, the coding function C that maps A into B, this B star is all finite sequences of the elements of B. So what does that mean? Well, oops. Okay. So if A is an example, the empty set A and B is the empty set 0 and 1. So what are the possible sequences of A? We have to be a little bit more formal about this, so we use a non-commutative function called cat for catenate, and if you have cat of A, B, 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 then that means the string A, B, B, B. And it's obviously not commutative because cat of AB is not equal to cat of BA. And that's the, if you remember from multiplication and addition, 2 plus 3 is equal to 3 plus 2, and 2 times 3 is equal to 3 times 2. Those are commutative functions. Okay, so our sequences here are just up to length 2. So all possible combinations are AA, AB, A, BA, BB, etc. And similar for B. So we can create a morphism. We talked about morphisms in some detail last week. And there's a isomorphism called C star that maps all messages from A into the messages of B. So if A is a finite sequence of elements, then the encoding through the function C star, A star into B star, given by all of these characters in A, you do the catenation of using the C function on each individual character. In order to make that work, we have to have C star be injected. Let's see, who's on my list here? Steve
I'm here.
Would you tell me what an injective morphism is?
I definitely remembered from last week, but I can't give you the definition. I'm sorry.
Okay. Art? Art. Is there Art on the line? I thought it was. Okay, let's move over. Pat King. Do you remember what a injective morphism is? Miguel, do you remember what an injective morphism is?
Are you out of your mind?
Do you know what a morphism is?
I think you just had it previously, didn't you, on the previous slide?
Yeah, it's a mapping. It's a way, you can think of it as a table. So all of the elements in A are on the left and all of the elements of B are on the right. And there's a table that says A1 goes to B1, A2 goes to B2, etc. That's a morphism.
Okay.
It's a table that tells you how to take an element from one set of inputs and get the corresponding outputs. Injective, yeah. Okay, so here's an isomorphism. This is it's a bijective morphism in this case. And injective means one-to-one and into. Surjective means that all of the x's go into all of the y's. So there's one-to-one and onto, that is, everyone is connected onto this. So they're unique, one-to-one, they're onto, each one covers every other one, and but an injective one doesn't, there will be more y's than there are x's in the case of an injective, as opposed to a surjective one where everyone from y is connected. Okay.
I'm glad you remembered that.
Did you use the term, I believe you used the term into and then onto. Did you mean those did you mean those are the same thing, or are they different, into and onto?
No, they're not the same.
What is the difference?
So, okay, this is into, right here, this is an injective morphism. So every X is connected in some unique Y, but not all the Y's are connected to all of the X's. There's more Y's than there are X's. That's into. Onto is this way. Every element here is mapped into every element here. So this is onto, and this is into.
Okay.
So this is surjective or onto, and this is injective or into. And bijective or an isomorphism is injective and surjective. So those are the three kinds of morphisms that mathematicians call about all the time. Okay, so if the reason we care about this is because if C star is injective, then it's decodable, assuming no error. So for many purposes, we're more interested in the collection of codes for the, where am I here? Okay. We are collection of code words for all of the alpha A, then the coding function. And we often look at the code words of Morse code or ASCII code. And the difference is what we talked about already, the fact that ASCII is a fixed length, whereas Morse is a variable code, variable. Won't let me move it. Okay. So if we remember that A consists of all finite sequences of the elements of A, then the encoding function simply looks like what we said before. We catenate everything together. And we have just used the conversion or coding function C for each character in A in order to get the resulting sequence in B. So it is possible to have a variable length code that could not be decodable even if it is injective. So we said that fixed length codes, if they're injective, are decodable. But variable length codes are not necessarily, even if the coding function is injective. Okay, my internet connection is unstable. You probably lost my voice. So a variable length code may not be decodable even if C is injective. So, but there is a family of variable length codes which are decodable in a natural way. If B, we're going from A to B, if B, suppose let's say it's an alphabet, and we have a finite subset C of B, which is called prefix free. That means that there's a special symbol that you can always define to be a unique start of a code word. So whenever you see this symbol, W, in the initial sequence of the whole word in C, then that unique symbol, W prime, then the coding function is called prefix free. If every code in the C starts with that character. Okay, so it must have still be injected, but it doesn't. But it must have this additional property called prefix free. But if it is both prefix free and injective, then we can decode the messages on the fly. So suppose we have this set of translated codes, B1, B2, etc. Then we know that the first message was A1 because that has the prefix free BW be W prime. So you can always proceed to look for the second code of the message once we know that the first one tells us the beginning of the set. Now this all assumes no error, and we're assuming perfect transmission. But if you're decoding this, once the signal's been sent to the other end, then you will be able to say, oh, this is the beginning of a new symbol, and then you can figure out which one of the finite set of conversions, the morphism that C star creates by following each of the following letters and finding until you find the one that's identical in the list, and then you know that the next one after that should be the prefix free character again, so you can check that you have it correct, and you now can, from defining by looking through all of possible there, you can decode, go backwards into the list. Okay, so here's an exercise. We let A equal 0 through 3 and B be 0, 1. And we have...
The audio's gone.
all right, can you hear me?
Well, you're popping in and out. About the only thing I could suggest is everybody else have their videos on?
Yeah, it would help if you would mute your video as well as your audio.
Yeah, because I think the tube in and out of your place is, that's an issue. And if ever you got to get all the videos in and out, that may help just so we can hear the audio and get your screen.
Sounds like a good idea. So if everybody would mute your video, I'd appreciate it. If you...
How do we mute our video?
there is at the Zoom thing on the left where it says mute,
Oh.
The next one says stop video.
I got it. Thank you.
Okay.
My new computer has a little switch that you can turn your video off.
Huh. Okay. Well, so we have two possible codings here. We have C and C tilde. C goes, C of 0 is 0, C of 1 is 1, 0, C of 2 is 1, 1, 0, and C3 is 1, 1, 1. So C is, and the reversal of every one of those codes, that is C tilde of 0 is 0, C tilde of 1 is 0, 1, C tilde of 2 is 0, 1, 1, and C3 is 1, 1, 1. Okay. So if you take a look at this, could somebody tell me why C is prefix free, but C tilde is not? Fred, if you unmute yourself and explain to me why this works.
I'm afraid I can't explain it.
Okay. Does anybody else have an explanation? Okay. In this code, 0 and 1 are both prefixes. So a 0 is unique as a starting code. So that works. 1 you can always go and look at 1 0, 1 1 0, 1 1 1. So if you see a 1 and you see a 0, you know you're done. If you see a 1 1, you don't know. So you have to look at the next one. And if it's a 0, that's done. If it's a 1, that's done. So then you just start all over again. In this case, in C tilde, if you start with a 0, you don't know whether it's a 0, a 0 1, or a 0 1 1. And if it's a 1, you don't know if that came after a 0 or it's starting a 1 1 1. So C0 is prefix free, but C tilde is not. Now, C tilde is injective, but it's not prefix free. Okay, let's see. This is just going through the same how you do the decoding, and last week I showed a recursive function, actually 3 parts to it, and it would run through this kind of a list and show you that the results were of length 3, 2, 0, and 2. Actually 1 and 2. That's a typo. My apologies.
Bob,
Yeah.
on your previous slide, the difference between C and C tilde, how do you tell the difference? I'm guessing that if one has no prefix, it's C, and if the other has a prefix, it's C tilde. Is that the answer?
No, it's the way I explained it. 0 is a unique code in this one. And
I understand all of them except for the C and C tilde.
well,
I'm
this
sorry,
is,
C3 and C tilde 3. Those are the ones I don't understand. Those are the same.
yeah.
So how do you know which one it is?
Well, you choose one C. I'm trying to show that you can have 2 identical codes, or essentially the identical codes, but by doing them in different order, you make them prefix free and not prefix free.
I understand that, but what you've done with C3 is they're both identical. So the only way to distinguish between the two of them.
No, you don't distinguish between these. You choose either this one or this one. You need to take the elements of A and code them into the sequences of B. And there's 2 ways to do it here. One is called C, and the other is called C tilde. And it is not you don't distinguish between these. They both work. They both do a complete coding. But the question is, how do you decode it once you've coded it? And if you use C, you can decode this because 0 is unique, and a 1 always tells you it's one of the remaining 3 possibilities. And if you get a 0, you know you're done. If you get a 1, you don't know whether you're done. It's either this or this. But if you get a 0, you're done, you're here. If you get a 1, you're done, you're here, and now you start again. So the decoding process of C is prefix free. That is, you can identify uniquely how to decode it. But as I went through before, this one, you don't know as you're going through uh, the 0 works fine, but the 0, 1, when you get you don't know whether this is 0 followed by 1, 1, 1 or 0, 1. You can't tell the difference in this coding. So this coding, although it is injective, that is, you're able to take any symbol on A and map it into B star, the sequence of all possible combinations of 0 and 1. It is injective. It is decodable in the sense
sound.
that, sorry, hope it's back. Anyway, you can uniquely always tell whether or not the C is a code, is either a 0 or starts a code with 1, and then you have to look at 2, and then you have to look at 3. But in this order, when you do it, you can't figure out between 0 and 0, 1, whether that's a 0 followed by a 1, 1, 1, or a 0, 1, or a 0, 1, 1. So there's no way to use C tilde uniquely decodable. It's not prefix free, whereas
Bob,
C is.
Bob,
Yeah.
just a comment that might help. If C tilde 3 were simply a 1 instead of a 1, 1, 1, then it would be prefix free.
Yes.
Because
But you would again have the ability to uniquely define C3 and figure out all the 0 codes from that. But because it's 1, 1, 1, that's absolutely correct. Thank you, Bob. Very helpful. Very helpful. Does everybody understand now the difference between C and C tilde? They are both decodable. They both completely can be used to code A into sequences of B star, but C is prefix free. That is, you can always say when the code starts and figure it out immediately for the next set of bits and then start again. Whereas this one doesn't tell you uniquely what happens, because when you get a 0, 1, you don't know whether it's 0, 1, 1, 1 or 0, 1 or 0, 1, 1. All of those are possibilities, and you don't know which is which.
Mhm.
Okay, so C is prefix free, but C tilde is not. They're two unique codings of A into B star. That is true, and C star is actually injected. That's why it's a coding, but it is not prefix free. That's the point here. You can have the same codes that, uniquely do all of the things that you want to do, but you can't decode this one, but you can decode this one. That's the point of this exercise.
Mhm.
Bob,
Yeah.
Bob,
could you go back to the previous slide and just tell us what injective, tell us what injective means once more.
Okay, injective means into. In this particular case, it's actually onto. Injective, and onto morphism is also injective. So for every symbol here in A, you can take a coding of B using all of the elements of B. And in particular in B star, all possible sequences. And these are one possible way of doing it, and this is a different way of doing it. And one works decodable, but the other one is not decodable. So the fact that this takes every element of A into a unique code means it's injected. But the fact that it's not prefix free means that you can't decode this on the fly. And
That's a good question.
Yeah.
Okay. Good. Again, you got to go back to the previous slide, because what I thought Bob Lukuski said is for C tilde, if you made 3, if you made the coding for 3 and C tilde just a 1, then it would be prefix free. And you said yes?
Yeah, because
But what happens then if you got a 0 and then you got a 1? How would you know that that's not 1 or
no, I didn't. It is prefix free, but not injected. Is the problem if it's a 1? So it's
Well,
not codable. You can't uniquely. Well, maybe you can.
yeah.
Let's see. If you had 3 equals 1, if you got a 1, you know you're done. If it's a 0.
But if you got a 0, 1, how do you know it's not 0, 3 coming in?
I'm sorry?
If I got the code sent to me and I got a 0 and then I got a 1, if C3
Oh, you're right.
was,
You're right. It still doesn't work. It's not injected. You're right.
yeah.
Okay.
And I think when I first, because I actually tried to study this after last week, what's confusing when you just show this is, and you're trying to interpret this and understand the distinction, in reality, what you're getting is this string of zeros and ones, 1 1 0 1 1 0 0 1 1, and that's what helped. If you think of it that way, that's what helped me at least understand the difference between these two and how one is unique and one isn't unique.
Yeah. I'm sorry. I thought Bob had that correct, but he did not. So I apologize. I got that wrong. He got it wrong and I got it wrong. I usually trust him. I should not do that.
No, let me go back to this. If I'm reading and I get a 1, then that translates into C3. So I know exactly what it is.
Yeah, but if you get a 0 1, you don't know whether it's a 0 followed by a 3 or it's a 0 1
no,
or a 0 1 1. It doesn't work as a coding. Won't decode.
Okay. Lots to think about.
What's the concatenation? You got to think of a whole string of these numbers coming in.
Right. Think of a 1 0 1 0 1 kind of thing. All right. The first 0 is unique, but the next 0, you don't know whether it means a 0 or a 0 1 or a 0 1 1. Or is it a 0 followed by a 3? That's why it doesn't work.
Let me take one more crack at this. If I get a 1, then I know.
Don't worry about it. If it's a 1, that's unique. That's fine.
Okay.
But a 0 is not then.
No,
because you could either be a 0 or it could be a 0 1, which means it could be a 0 or it could be a 1 or it could be a 0 followed by a 3. It won't work.
Okay.
Got it?
Yeah.
Okay. Thank you.
Bob, why would anybody use the C tilde tilde code as opposed to the C code? Because it requires more characters, therefore taking longer. Why would anybody even
Well,
use
no,
it?
you have to add a space character into this in
Right,
order.
a space character or a
Right.
delineation character.
You wouldn't. I'm just simply trying to give you some understanding how different codings work. And
Oh, okay.
prefix-free ones mean that you can instantaneously decode. You can use it on the fly, but the non-prefix free codes are the like C tilde mean you have to add a special symbol in there in order to separate each code. You're back to the Morse code.
Mm-hmm.
Okay. So I just wanted to point out that even though the two codes are unique, they completely map everything in A into B star, but they are not decodable. They're not prefix free. They're not instantaneously decodable. That's the point of this exercise, is for people to realize that even though you can have two codings that are unique, but one will work instantaneously, the other will not. You need to add an extra symbol in there to tell the difference between them. Okay, and we went through this last time. I'm not going to do it again. Okay, the Morse code is a binary code, but not prefix free because, as I said, E goes to dot as a prefix, but S has the same thing, and you can't tell the difference between the two. So that's why the space symbol was added in order to be able to tell between symbols. That's what we just discussed and showed in the C and C tilde stuff. So I'm going to assume from here on in that we're using a prefix-free coding. Okay, telegraph was expensive to build and use, and you had a limited number of symbols that could be sent for each minute. If you were getting your ham code, as I said last week, you had to be able to type at least 25 characters a minute in Morse code using a key. I could never get there, so I never got my ham key. They've dropped that now, so you can do it much easier today. I could probably get it now. Okay, so the reason for making it variable length was to use the shortest characters short and the longest characters long. So in the E, it was simply a dot followed by a space, while the Q was dash, dash, dot, dash. So it's possible to increase the rate at which symbols are sent and received using machines. But there are limits on the number of symbols that can be correctly transmitted over every given line. And we talked about that in the channel capacity theorem of Shannon. So, and in particular in the undersea cables, those were the slowest rates being, sorry, okay. So telegraph companies usually charge so much a letter and also so much a word, or often just so much a word, with a limit on the permitted word length. So often, if you were doing, you can go to Google for telegraphic codes and message practice, and they'll tell you about all these things. So to save lots of characters, you'd send FTCGI meant, are you willing to split the difference? While FTCSU meant, cannot see a difference. These are just, of course, made up words that people agreed on, and that was called the telegraph wording, I think. Well, I forget, there's a name, right? For the type of language that people sent messages using. Anyway, but today we don't use the old-fashioned Morse code. We use binary sequences. But each transmission still costs of a bit, costs money. So if there are n possible messages that can be sent, and if n is less than 2 to the m, we can assign each message a different string bits in each message. So the message will cost the m, the number of bits, times the cost per sending 1 bit.
You're going in and out for me.
Okay, yeah, I saw my message go unstable, so I paused. Okay, this may not be the best way of saving money if you make them all the same number of bits in the coding. You often, one message such as nothing to report is much more frequent than any other, and it would be, you would want to be cheaper on average to assign it a shorter code length. And even though other less likely messages that had cost longer than the average length of the codes. So by making them variable length, you can potentially shorten the number of bits that you're going to use, and hence the actual cost. So given n messages such that the probability of each is pj, then each, the cost will be the cost per bit times the expected probability times the number of bits used in each message. So if this is minimized, that will minimize the cost. And in 1951, nobody knew the answer to this question. How do you write a code that could minimize the cost of a set of messages? Huffman was at the end of his university exam in some course, I don't remember which one it was. Anyway, he was asked to write an essay on this problem. Instead of writing the essay that he was asked to do, he just solved the problem and wrote it up, surprising his professor, obviously. So in his algorithm, and this is the part we're getting to that I wanted to do again because it was, I did a bad job last time. The following algorithm solves problem 3. That is, they minimize the number of bits. Yeah, there's problem 3. Minimize this expected length. So he said, start by ordering the messages. So the P1 is the most likely down to the least. Solve the first problem by choosing the lowest probability one. And then once you have that, you select the first Pn and Pn minus 1 and make a new n minus 1 message, which takes the catenation of mn and mn minus 1. And then solve the problem again using, that is, resort. The probabilities will be the sum of the probabilities, and those will fit somewhere in the sequence, not necessarily between Pn minus 2 and then Pn minus 1, whatever it is. You have to figure out that part of it, and then you have to, again, solve it going backwards and keep repeatedly doing this process. So when n is 2, the problem is obviously 0. You choose m1 equals 0 and m2 equals 1. And it's longer, you have to use a recursive solution, which is hard to think about. We talked about it last time, such as factorial. So factorial is 1 times 2 times 3 ... times n. So 6 factorial is, I'm sorry, let's do something shorter than that. I can do 4. So 2 times 3 times 4 will give you 6 times 4, gives you 24. So that's 4 factorial. If you do it recursively, you say that the factorial of n is equal to n times factorial of n minus 1 until you reach 1, at which point you stop the process saying that it's 1. So you get 4 times factorial n of 3. Factorial of 3 says it's 3 times factorial of 2. Factorial, which is factorial of 2 is 2 times factorial of 1. Factorial of 1 is 1. So you now go back to the 2 times 1, drop it back again to the 3 times 2 times 1, and go back to the 4 times 3 times 2 times 1. So it gives the same result, but I just wanted to try to explain what a recursive function is. And these were the functions actually initially described by, who was the great cryptographer from World War II. Oh, I'm losing my mind. Sorry. Can somebody tell me?
Was Turin somebody?
Yeah, yeah. Okay. Anyway, he's designed these recursive functions, and there's a whole computability theory of mathematics based on recursive functions, but we aren't going to go there. So suppose we have n equals 4, and that is, there's 4 messages, and each of those has various probabilities: 0.091, 0.293, 0.386, and 0.23. So, and we're going to say that these are A, B, C, and D. Okay? So here's what our solution looks like. The first step, you sort everything in terms of increasing, or I should say in decreasing probability. So you start at the bottom at C at 0.36, B is 0.293, D is 0.23, and A is 0.091. Okay, so you have a 0 for the lowest probability one and a 1 for the next one. At the beginning of code step 1, you have A equals 0 and B equals 1, and the rest are unknown. And you map to for the next set, you use a different set of messages. You have C at 0.386, AD is 0.321. If you add the 0.091 and the 23, AD gives you 321. And B is less than that, so B has 0.93. And this is the symbol set that you're going to use in the next step of the process. Whoops, sorry. Okay. So there, that's the one. I went to the next slide instead of going to this. So we now have our character set C, AD, and B with these probabilities in this order. So we had the previous one before, 0 and 1 on B. We add a 0 to the B and a 1 to the AD. And because those are the two. So the C remains 0.386, and you now concatenate all these characters together, BAD, and those, when you add them together, are 0.614. So C in this case is less than BAD. So now you always work these backwards, as we said before. So we had a 0 and a 1. Now, sorry, I lost voice again. All right, so we have a 0 and a 1 from the previous step. And we have a 0 on the B, so we put that there. And we have a 1 on the AD. So we put a 1 on the A and a 1 on the B. And our next set of letters are going to be C and BAD, and they're going to have these probabilities. So you have these two, it's 0 and 1. And of course, now you're going to go to CAD, which is all the probability on that. So the code for step 3 was before 0, 1, 0, 1, 1. And now you add for A, a 1, for B, a 1, for D, a 1, and the C gets the 0. Okay? So you're done because CBAD now has probability 1. There's nothing left to do. So these are the codes. The Huffman code says that A will have 1, 1, 0. D will have 1, 1, 1. B will be 1, read them this way. Sorry, I keep doing that wrong. A will be 0, 1, 1. B will be 0, 1. C will be 0. And D will be 1, 1, 1. Okay. So as you can see over here, we reorder things and we keep adding pieces onto it. So hopefully this makes it much easier to understand how a Huffman code works. And just to do this, when you get there, I should have had another step in here that had this shown up, but the highest probability is C. So it only gets a 0. On the other hand, the next highest is a B. So the B code is a 1, 0. And the one after that is the D, and the D gets a 1, 1, 1, and an A gets the 1, 1, 0. And again, the reason in which it's done in this order is to make it prefix free. This is the C injection that we talked about last time in the previous example. So hopefully, could Patrick, would you tell me whether or not you understand what happened in this?
Yeah, am I on the air? Yeah.
You're on the air.
Okay. Yeah, I can follow you. Unfortunately, the basic terminology, I saw what you did, and it looks very nice. You ended up with a few slides back, a C code.
Yeah, I actually
prefix
used
prefix free
right
code by doing this.
And I had actually the highest probability character only had 1 bit.
Yes.
The next highest probability one had 2 bits, and the 2 highest probabilities had 3 bits. So I'm claiming that this minimizes the average cost on these.
Yes.
Okay.
It's very, very nice. As I said, I'm way behind on the terminology, unfortunately.
Okay.
But I see exactly what you're doing. When you go to detect this code, does this mean prefix free that you don't need any kind of telling you where to start detecting. Is that
Right. It's instantaneous decoding.
yeah?
Because if it's a 0, it's unique. It's just a C. If it's a 1, you need to look at the next code, the next bit. And if the bit is a 0, this is unique. It's a B, 1 0. If it's not, if it's a 1 1, it could be an A or it could be a D. So you have to go to the next bit, and you can choose by the third bit whether it's an A or a D. And then you just, once you have discovered whether, what the message is decoded, here you start the process again. And it's always either a 0 or a 1. And if it's a 0, you're done. If it's a 1, you have to look at the second bit. And if the second bit is a 0, you're done. If it's not, you need to look at the third bit. And if it's a 0, it's an A. And if it's a D, it's a B. So, and then you start the whole process again. Yeah, you do it again.
Yeah, I like this. I'm a little. I want to find out how. Once you know where the sequence of 0s and 1s start, you can then start interpreting this way, looking for these patterns. But do you need to start the code originally, knowing where it starts? You can't just jump in on any old code.
No, you can't. You have to start from the beginning and decode each one. But the assumption is we're in a channel. You've got a message which has a sequence of characters. Those characters are coded. The coded set of messages are transmitted in a channel, and the receiver receives them. We're making the assumption that there's no noise and no distortion. And we can use this kind of a code to take any message out of ABCD and code it into a sequence of 1s and 0s that if we've assumed no error, no noise, no distortion. So we can transmit the symbols exactly. At the other end, you've got the string of 1s and 0s, and we've talked about how to decode them. Okay, there's another way to look at this. You can use a tree, and this is an identity. It's an isomorphism to the code I just talked about. So the way in which you do this is you look at you start up here with the C has a 0, and the left has always got a 0 added to it. And the right always has a 1 added to it. So the C gets the 0. When you get to this, you don't know what the answer is, so you've got a B. This has got a 0, 1, and this has got a 0, 1. I'm sorry, a 1, 0. And then you get A is a 0, 1, 1, and a D is a 1, 1, 1. So this is a different way of mapping the same set of codings. Some people like this version better. In either procedure, you can always say that an A will give you, as I said before, 1, 1, 0. A B will get a 1, 0. A C gets a 0. D gets a 1, 1, 1. And these intermediary steps, S1, 2, and 3, get those, although just for reading the tree. Okay, so let's take a look at an example. Suppose we use this, we took the probabilities that I had before into the 4 characters, and then took a 500 random string with the same frequencies. And it's, of course, much longer, but I just cut part of it out. Then you can decode it using our Huffman code, the same code we just had before. So you get this, you take that 500 random characters from A, B, C, D, which follow the same frequency as the probabilities I said before. You make them into a string which has 929 bits. So you had 500 characters, and now you have 929 bits. Now, since there's only 4 characters in this, we could have used a 2-bit code, because 2 to the 2 is 4, and that'll map, that will give you a fixed length coding of A, B, C, D. So if you took the 2-bit code that I just talked about, the fixed size code, and you had used them to code the 500 random string, how many bits would it have used? Somebody want to tell me? Hint, the answer is footnote 10. All right, it's
2 times
1,000.
500. 2 times 500. How about that?
How about that? Right, 1,000 bits. We just had said it was 929 bits in the Huffman code. So the Huffman code beats the fixed code by 71 bits. And it's also, that's also the lowest number of bits that can be used to decode that at any cost per bit. Okay, so hopefully now you can understand how human codes work, how, I'm sorry, that was supposed to be Huffman codes. I obviously typed that wrong. And these codes are prefix free, and they decode continuously without a space code. They're instantaneous codes. We can block these into a continuous code with fixed block size. So all of this so far assumes no noise and distortion. We want to start taking a look at what happens to error correcting codes. Okay, so optical discs, computer operating systems, communication with spacecraft billions of miles away, like Voyager 1, still sending at its incredible rate of 22 bits per minute. It is amazing that you can still actually receive the messages, and it's outside of our solar system. So it's one of the most amazing and underappreciated results of science, in the science of information. And it begins with human language. Human language appears to be very inefficient, as I described a couple of lectures before, when we analyze the statistical properties of English language. If I analyze the text letter by letter, I find that the letter entropy is nearly 5 bits, as the Bateau code was to use 5 binary digits per letter. And by analyzing the text word by word and taking into account the fact that words are very common and others are not, we talked about the zip distribution a couple of lectures ago. And you can find that the word entropy, the information content of each word, is less than 10 bits. So if you were to use each 5 bits on each, oh yeah, the average length of an English word is about 5 letters. So if you took 5 letters times 5 bits per letter, you'd get 25 bits to express a message less than 10 bits of information. So that would be very inefficient. Now, okay. English is short and very redundant, and the same thing is true of every other language. Every one of them uses more symbols than the message seems to require in terms of the letters of the text, or if you're speaking it in terms of phonemes. There's a different way to state the same fact. There are a lot fewer English words than you might expect. With 26 letters, the number of 5-letter groups is 26 to the 5th, approximately 12 million. I think there's a 0 at the end of that one, but I know it's got to be something else. I obviously typed that wrong. Anyway, how many actual 5-letter words are there? Well, one good source would be the tournament word list for the popular word game Scrabble, which somebody talked about with us once before. And that list contained about 9,000 5-letter words. Now, I need to retype that. Another coding error, sorry. 9,000 is much less than 12 million. There's many of those unused words that are completely unpronounceable, like OK MBF. Try and figure out what that says, like Okamufla, something like that. Not even if you only include pronounceable words, there are many more possibilities than English makes use of. Many of them are used in other languages. Okay, that's another talk. Okay, Vorby, not Furby. Furby is the toy a Furby, that Furbish, I'm sorry, is a language for Furbies that the Japanese made up in this toy. But Vorbi is not an English word, but it is Romanian. And in Romanian, Vorbi means to speak. So think of a vast space. Consider an axis with 26 letters on it, and then make a orthogonal second axis and a orthogonal third axis and a orthogonal fourth axis and an orthogonal fifth axis. Don't think about it because you won't be able to. At least I can't. But this vast combination of all these letters, this space is vast. There's lots and lots of arrangements because there's roughly 12 million points in that space. But since there's only about 9,000 English words, the English is scattered throughout that space very, very sparsely. So why do we use so few of the words? Well, you could ask the same question in a different direction. Why do we use fewer letters? Why don't we use fewer letters for words? That would make the space of possible words not so vast. There'd be plenty of room to fit our vocabulary into it, since there's only 9,000 that we need to do. But in fact, the redundancy of English is no flaw. It serves a vital purpose. It serves a vital purpose. It makes our communication much less subject to errors. So consider the list of 9,000 English 5 letters. Some of them are close together in the space of possible words. They might differ by only one letter, like pride or prime. So let's call those neighbors of each other. They're just one step apart. How many neighbors does a typical word have? If we're considering all possible 5-letter words, then each of the 5 letters might be changed to any of 25 alternatives. So the total number of words in 1-letter difference from our starting point, the neighbor of the word, would be 5 times 25. That's 125. So if you take a look at all of those, of course, only a few of those will be actual English words. So the word grove has about average with 6 neighbors. Drove, grove, grave, grope, prove, and trove. So on average, instead of 25 alternatives, there's really only 6 on average. So there's a nice word game based on an idea called doublets or word golf. And it was invented by Charles Dodgson, the 19th century writer and magician and logician, who under the pen name Lewis Carroll is most famous as the author of Alice in Wonderland. The game starts with one word, then stepping only between neighbors that is, only actual English word changes in step by a character in each step. It's called word golf because the idea is to reach the goal in the fewest number of steps. And you can, so as an example, can you turn head to tail in just 5 steps? Lukowski.
Well, I can see on the bottom that you've done it.
Yes, I always try to make it easy for you.
So the answer is yes, you can.
Yes, you can. Head goes to heel, goes to teal, goes to toe, goes to tall, goes to tail. So, as I said, most words only have a few neighbors, typically 6. And that's what makes word golf more of a challenge. And but that's also why English is resistant to corruption by errors. So suppose somebody sends a 5-letter word, but for some reason, electrical noise in the telegraphy, sloppy handwriting on the page, there's an error of, there's an error that occurs in one letter. So we've said there's 125 possible changes, but only 6 on average. The probability is better than 95% that the error is obvious. 6 over 125 is less than 5%. So the probability that you're going to pick which one of those it is, it's fairly obvious that the error is noticeable. And this is how computer spell checkers work. Although they're more, we do it intuitively, but they use Markov models, hidden Markov models. That's the word I was looking for earlier. Okay. If the word is part of a larger message, the likelihood is also very high that the surrounding context will be able to figure out the right word in spite of the error. So an error that occurs in transmission, we can be able to correct the error as we read it. What is true for written text is also true for spoken language. And the error in speaking and hearing, especially in a noisy and distracting sound environment, is quite high. Not for me, because my hearing is almost miserable, but for most people, you can, even at a party, you can generally hear what other people are talking to you. All right, so because English is so redundant, a few misheard phonemes are usually no problem. The hearer corrects them automatically and unconsciously, actually. Error correction wouldn't work as well if English words were more crowded together in that space of all possible words. So 9,000 out of 12 million. So the mistake of a letter or sound would more likely turn, a mistaken letter or sound would more likely turn the correct word into another plausible word, but misunderstandings would abound. So the important result is that in the real world, error correction is important. Redundancy is not a bug, it's a feature. In one of the previous lectures, we saw how Shannon's second fundamental theorem guaranteed that error correction is possible, provided that enough of the information in some channel was allowed to get through. So the amount of information conveyed by a channel is its mutual information, which we talked about, callback distance and mutual information. And the maximum mutual information for a channel is called its channel capacity, C. If we're clever about inventing a code and our decoding procedure, then in the long run, we can send up to C bits per use of the channel while making the overall probability as small as we want to. However, even though Shannon's theorem guarantees that the error correction is possible, again, another footnote that I mistyped. It's what mathematicians call an existence proof, not a constructive proof. So Shannon's theorem proves that it's possible, but it does not tell us how to go about it. We're going to move on to that next. So in the years since information theory in 1948, many mathematicians, computer scientists, engineers, and even a few physicists have worked on designing error-correcting codes for various situations. Error-correcting codes are based on the same idea we encountered when discussing redundancy of English. We use a longer code word, and that code word in our code will be scattered sparsely in the set of possible code words. So we're going to lengthen the number of bits that we're going to use in order to be able to understand what's happening. The code words in some sense, the sense will be defined in a while for the Hamming distance. Those code words will be far apart from each other, and it will be easier to recognize and fix potential errors. So let's start with the simplest possible error correcting code. Okay. Alice wants to send 1-bit message to Bob, a 0 or a 1. However, there's some probability that an error is made when the bit is transmitted. So Alice uses code words consisting of 3 bits. She simply transmits the same bit 3 times. So if she wants to send a 0, she sends 0, 0, 0. If she wants to send a 1, she says a 1, 1, 1. However, of course, Bob, because there will be noise, might receive some bits incorrectly. So he checks to see if there are more 0s than 1s. And if there are more 0s than 1s, he decodes it as a 0. And if it has less zeros than ones, he decodes it as a 1. So here's the first basic question. Does this actually help? So sending more bits does make it more redundant, but it also makes a higher opportunity for errors. So will this method actually improve Bob's chances of decoding Alice's message correctly? Let's suppose that each bit transmitted has an error probability E, and we'll take it to be 5%. For that probability of error, if Alice sends 1-bit message once without using error correction. On the other hand, if she sends 3, and we're assuming that they're all equally likely and independent, that is a Poisson process, then the probability that a bit is transmitted correctly is 1 minus E, or 95%. Now consider that Alice's repeats them 3 times. The likelihood that Bob receives each of the 3 bits is 1 minus E times 1 minus E times 1 minus E. And the probability that all 3 are sent is 0.857. So Bob will also decode the messages correctly if just 1 bit is wrong. There are 3 ways in which that can happen. The first bit, the second, or the third bit could be the wrong one. So for each one of these, it has a probability of 1 minus E squared, 1 minus E times 1 minus E times E. 2 rights and a wrong, which is 0.95 times 0.05, or 0.045. The total probability that Bob recovers the original 1-bit message is therefore 0.993. So Bob has a better than 99% chance of getting Alice's message right. So we went from a 5% chance to a better than 99% chance. So error correction does help after all. Hamming distance. We can visualize how the code works. The 8 possible 3-bit words are arranged on the corner of a 3-dimensional cube, shown here. We can define how far apart 2 code words are using the Hamming distance, named after Richard Hamming, one of Shannon's colleagues at Bell Labs and a pioneer in error correcting codes. So going from 00 to 001 has 1 distance. 0 to 010 also has a distance 1. 000 to 100 has a distance of 1, but a distance from 00 to 011 goes 1, 2, so it's length 2. So the Hamming distance between 2 code words is the number of places in which they differ. So 0, 0, 0 has a distance 1 from 1, 0, 0, as we showed before, and a distance 2 from 1, 0, 1. Here you go from 0, 0 to 0, 1 to 1, 0, 1. So this is 2. And has a distance of 3 from 1, 1, 1. So you go from, where's 1, 1, 1? There it is. Okay. So you can, there's many ways, of course, to get there, but you can go this 1, 2, 3, and any other path that you go through will always take 3. So the Hamming distance between any two code words is the number of places in which they differ. And here is another example showing two possibilities, 0 to 1, 0, which has got a, I'm sorry, what we got from 0, 1, 0, where is that? 0, 1, 0 to 0, 1, 1. That, no, that has a 1, oh, I'm sorry, 1, 0, 0 to 0, 1, 1. You've got several ways to go, but you can go here, here, here. That has a distance 3, whereas come on. 0, 1, 0 has a distance to 1, 1, 1. Has a distance of 2. So hopefully, pause, internet instability. Okay, so hopefully you can see from these pictures how Hamming distance works. So, two code words Alice's uses are 0, 0, 0 and 1, 1, 1, which are separated by a Hamming distance of 3. And that's the significant number. If Alice uses the code word 0, 0, an error that occurs in 1 bit, Bob can if there's any 1-bit error in the code for 0, 0, 0, he'll simply count the number of zeros, and if there's 1-bit error, he'll show 1 has a 1 in it, but there's 2 zeros, so he'll just say it's a 0, 0, 0. And if it were a 1, 1, 1, then he'd do the reverse process. He'd count the number of 1s. There's 2, so he'd say it was a 1, 1, 1, which he knows means the original 0, 0 has a 0, and a 1, 1, 1 has a 1. So with 1 error and 3 bits sent, you can always find the short Hamming distance 1 to the alternative 3 for 1, 1, 1. So the code word separated by distance 3. I just said that, sorry. Whatever Bob receives, he shifts it back to the nearest code word in Alice's code before decoding messages. So let's see.
I have a question.
Yeah,
Okay, Bob shifts it back to the nearest code word in Alice's code because he has 3 potentials. He's
yeah,
received 3 codes. And I guess he chooses, you know, if 2 out of the 3 are the same, then that's the one he chooses.
yeah,
Okay, what about now? You talked a few slides back. You gave us, I think, a 500-bit example.
right.
And then you were talking about how to cut down on the number of bits transmitted. Well, okay, so you were successful in cutting it down by substitution. So now what you've done is you've increased the number of bits by 3.
Yep.
So what about time and cost?
Well, the question is how much noise and distortion is in the channel you're using to communicate. If the signal to noise ratio is very low, that is, you can almost, like 0.999 receive everyone's correctly, then you don't need error correction. And it's actually more like 0.999999 in order to do that accurately with long strings. But the point is that even though you increase the number of bits, the fact that you can correct them automatically means you don't have to resend the message. If you have too much noise, you're going to have garbled messages sent, and you have to ask them resent. And that, of course, more than doubles not an individual character error, but the entire message. So twice times the message cost is much higher than 3 times a letter error. Did that make sense?
Yeah.
Bob,
Okay.
it's 12 o'clock. This looks like you're just getting into a new topic here. And it might be a good
Yeah,
break.
I was trying to get to the actual mathematics of it and how these codes work, but we got a little ways to go. So I'll pick it up next week with where we are. Maybe do a very small amount of time on cryptography, and then we'll move on.
I can't hear you.
Oh, sorry. Can you?
Yeah.
Pause. I keep getting these unstable internet messages, so I try to stop whenever they come on my screen and then say pause a couple of times before I move on. That just tells you I saw the signal say it was unstable. Anyway, next week, as I said, we'll go back and finish on the Hamming distance and the types of codes. We did a very simple version, a 3-1. You can do different kinds of codes. And as I said, we'll probably do a little bit on cryptography, although a very small amount. And then that'll probably, for us, finish this. There are many other kinds of error correcting codes than Hamming codes, but those are the easiest to understand, and we'll finish those up and then move on to something that I've been trying to get to for 11 lectures, now 12.
Don't hear you. Okay.
Um, I'll be moving on to how thermodynamics actually is based on information theory. We'll need to go through some preceding material. Hamilton flows, which you've actually seen, but you didn't realize it at the time when we did Louisville's theorem. So we'll go back about Louisville's theorem, and we'll talk about Hamilton flows, and then we'll talk about the most interesting idea that has come along in a long time, Ido states. These are not, Ido states. They're a non EIDO, and they're unique states for systems, and the combination of the two turns out to be the basis of thermodynamics. So you can actually, using the Slizard engine, Hamilton flows, and Ido states, develop all of thermodynamics using information theory that we've talked about here. So I've got probably, hopefully, no more than 2 more lectures left, 3 at most. And then somebody else is going to have to take it over, because I'm going to be starting my quantum field theory with Kathleen and Steve, and that's going to be taking full time, because we're going to be doing real mathematics in this, and I won't have time to do more lecturing. So people should start thinking about who they're going to take over for the next couple of months in lecturing. And we'll talk about that over the next 2 or 3 lectures, and somebody will have to take it over after that. Okay.
Well done. Good. Very, very interesting lecture today. Appreciate it.
Okay, thank you. All right,
Well,
let's see. I need to stop the share. I need to